Okay, now's the section where we start putting this together. We've got the student's t-distribution, and we've got the how to estimate population means if we know the population standard deviation, and those will combine to give us a way to do estimating these population means if we don't know the population standard deviation. Basically, all we do is use the critical t-scores instead of the z-scores. There are a couple of criteria we have to meet to do this. First off, it's got to be a simple random sample. We can't know the population standard deviation. That's usually a fairly easy one to meet. And we have to be able to apply the central limit theorem. So the sample size has got to be at least 30, or the population distribution has to be approximately normal. If that is the case, we can use this formula, which is almost identical to the formula we used 2 sections ago. We've got the critical t-score now instead of the critical z-score. We have the sample standard deviation instead of the population standard deviation. Otherwise, it's the same. So we've got sample standard deviation divided by square root of sample size times the critical t-score. Again, that critical t-score is associated with some confidence level. So we're looking at the confidence level, subtracting that from 1 to get the amount that, if we're 90% confident that it's in that our population mean is in this area. We're 10% confident that it's outside of that area. It's that 10% that is the alpha. We have alpha over 2 is the two-tailed version, or the smaller number. Okay, so let's look at some examples. All right, let me pause and put this cat out of the room because it is just going to drive me crazy otherwise. All right. Okay, so if we've got some dental researchers who are trying to estimate filling material leakage in nanometers for cavities using a simple random sample of 10 trials. We're going to assume the population distribution is approximately normal, and we don't know the population standard deviation. We want a 95% confidence interval for the population mean, and we have the sample standard deviation as 15.5 nanometers. Okay. First off, we know the population distribution is normal, or at least we're assuming it is. We don't know the standard deviation, but because that's approximately normal, even though our sample size is only 10, we can use the t-distribution. So we've got the values for S and N from the problem. 15.5 was the sample standard deviation. 10 is our number of trials, number of samples. So the only value we're missing is that critical t value. Confidence level is 95%, so alpha is going to be 0.05. Right, 95% is 0.95. Therefore, alpha over 2 is 0.05 over 2, or 0.025. Sample size of 10 means there are 9 degrees of freedom. Degrees of freedom, again, is sample size minus 1. Okay, we can find this by hand using the t-distribution tables. You can look at the row for 9 degrees of freedom and the area in one tail of 0.025 or the area in two tails of 0.05. Either one works. Both give the same answer, right? There's 0.025 or 0.5. You see they're stacked right up, so it's the same column. 9 degrees of freedom, 2.262. Again, we can also do this in the calculator. There we have to give it the 0.025. and we get negative 2.062 to negative 2.262. Sorry. We want the positive value, so we can just ignore the negative sign. It's symmetric, so we can kind of do that. It pays to take a little bit of time and think through if you're after the positive or the negative version. It may help to sketch a little distribution to see what you're help think through that. It's always helpful to sketch things out to help think through things. All right, if we put these values into our margin of error formula, right, critical t-value, sample standard deviation, sample size. So 2.262, 15.5, and 10, we get 11.087262. They've rounded it 6 decimal places. Honestly, for presentation, I would have rounded it less, left it unrounded for further calculations, but probably not. Well, yeah. So the confidence interval, as we've already discussed, is the sample mean plus and minus our margin of error. Okay. So if we're looking at a marketing company and we want to think about the mean price of new vehicles sold in a growing area of town, we've collected data over 2 years from all the dealerships in that area and looked at new car sales. And we think the population distribution looks like this. So this is a tails off to the right. It's left skewed, right? I have already forgotten if it skews towards where most of the, it skews towards where most of the area is, not towards where the tail is. Okay, so it's left skewed. It's not a normal underlying distribution. If they've taken a random sample of 756 car sales, that sample has a mean of 27,400 with a standard deviation of 1,300. They want a 95% confidence interval for the mean price of a new car sold in this area. All right. We've got our point estimate as the population mean, and of the population mean as the sample mean, which were given as 27,400. We need to find the margin of error. We know that it's likely not normal. Okay, it's skewed to the right, so I was wrong. It skews towards the tail. I knew that 2 weeks ago. Doesn't matter right now, though. Sample size is sufficiently large that we can use the student's t-distribution for the margin of error calculation, because 756 is quite a bit larger than our minimum of 30. Sample standard deviation is 1,300, so S is 1,300. All that remains is to find that critical t-value. You're after a 95% confidence interval, so from the previous example, that's 0.0 t sub 0.025. 756 minus 1, or 755 degrees of freedom. Again, degrees of freedom is sample size minus 1. Now, because the table starts skipping around quite a bit at that point, looks like we got 400, 500, 750, and 1,000. So I could use the table and look up 750. It would give Okay. So they've gone ahead and put it into, excuse me, put it into the calculator, and got a critical t value of 1.963, which is, yes, it is. It is the same value as in the table for 750 degrees of freedom. Um, there are probably differences much farther out. There's 1.9631109. So there's differences probably somewhere out here. But there's no differences in the first three values. So putting that into 1.963 into our margin of error formula, again, E is the margin of error, critical t value, sample standard deviation, sample size. So 756, 1300 was our sample standard deviation, and 1.963 is our critical t value. We get 92.811706. We add and subtract that from the margin of error. To get the lower and upper endpoints. So our lower endpoint, subtract that margin of error, round to the nearest dollar. We get 27,307. Upper endpoint, rounded to the nearest dollar, 27,493. So 95% confident that the price of a new car in this area ranges from 27,307 to 27,493. I would guess that this would probably be reported as 27,300 to 27,500, to be honest. But yeah, it can be written either with less than signs or as a range like so. If you're writing it as a range with interval notation, it might be clearer to leave off the commas because that looks like a string of 5 numbers instead of 4 numbers. Yeah. Okay, so if we're looking at costs at a local computer repair shop, um, looking at 20 randomly selected repair jobs. There we go. So our sample size is 20. Our mean is 216.53, and the standard deviation is 15.86. I'm going to assume the population distribution is approximately normal, and the population standard deviation is unknown. So our sample size is 20, which is less than the 30 we need, but with the assumption that the population distribution is normal, we can proceed. So we're after the 98% confidence interval for the average repair cost for all computers at that shop. So let's calculate the margin of error. And then use the calculator to determine the confidence interval from those statistics. Okay. We're given the assumption of normality, so we can proceed. Our point estimate is the sample mean, which is 216.53. Margin of error, first we have to find that critical t value. Confidence level is 98%, so alpha is going to be 0.02, right? 1 minus 9.98 is 0.02. Alpha over 2 that we're looking for is 0.01. So I'll be using 0.01 in the calculator formula, or looking at the 0.01 column in the one-tail value of the table. And we had 20 computers, so we have 19 degrees of freedom with sample size minus 1. we find that our critical t value is 2.539. Right, to find the margin of error, we plug our values into the equation. 2.539, 15.86 was our sample standard deviation. Sample size is 20. It is important to remember that this is sample size, not degrees of freedom. If you're moving along too fast, that would be an easy mistake to make. So our margin of error is 9.004319. We add and subtract that from the point estimate to get our confidence interval, right? And our lower endpoint. So there's our sample mean minus the margin of error gives us 207.53, and plus the margin of error gives us 225.53. And again, we can either write it as an interval or an inequality, either way. Let's do the same calculation with the TI-83. So it's got this t interval function built in. Tell it you wanted stats because we were given sample statistics. Put in the mean, sample standard deviation, which is capital S, lowercase x, sample size, and confidence level, and tell it to calculate, and it will spit out the interval, 98% confidence interval there. All right, so let's look at this one. We're given sample data about amount of water used per day by members of a household while brushing their teeth. I assume this is whole house water values. We want the 99% confidence interval for the population, and this is all going to be done in the using the calculator. Let's assume it was a simple random sample. So here is our data. We're not told any population parameters, so we can't assume that that the population standard deviation is known. We also don't know whether the underlying distribution is approximately normal, but the sample size is large enough, because that's larger than 30, that we can use the t-distribution to construct our confidence interval. So to begin with, you'll have to enter all the raw data into the calculator list. Using those directions. Once you've got the data entered, go to tests, choose the t-interval, choose data instead of stats this time, specify which list you put your data in, and the confidence level, leave freq as the default value. That probably stands for frequency. I'm not sure what it's used for yet. I imagine that will come up. Then hit calculate, and you should get these results. And again, we can write that either as an inequality or using interval notation. Means that we're 99% confident that the average amount of water used per household for brushing teeth is between 0.524 and 0.7624 gallons per day. Okay, that is the end of that. We will cover estimating proportions for a confidence interval for proportions, and estimating the population variance next week.